Okay, so in this set of lecture slides, we're going to be looking at Ohm's law, electromotive force, and motional EMF. So up until now, we've been looking at electrostatics, so stationary electrons. Now we're going to look at electrodynamics, where we're going to look at moving electrons. So what makes electrons move? Well, electric fields we know can make electrons move, and magnetic fields, if they already have an initial velocity, they can apply an additional magnetic force. Thermal energy can also make electrons move. What we're going to be looking at least in this chapter, is electrons moving in an electric field. We know the force on a charged particle, in this case the electron, in an electric field is just equal to the charge of the electron minus E times the electric field that the electron is in. So Ohm's law states that the current density, J, for most materials is proportional to the electric field or force per unit charge of an electron. So the current density is equal to some constant of proportionality that we'll define times the electric field. Okay. This is called Ohm's law, where this sigma is called the conductivity of the material. You can also define it in terms of the resistivity of the material, which is defined just as 1 over the conductivity. So we're not going to derive Ohm's law in this class, but we did do it in solid state. So you can look back at your notes from solid state to see where Ohm's law comes from. But for now, we just know that the current density is proportional to the electric field. So if you have a large conductivity, if a material has a large conductivity, it's a good conductor. If it has a small conductivity or a big resistivity, it's a poor conductor. So the first problem you're going to do is to find the current flow through a wire of certain conductivity and length, given the potential difference between the two ends of the wire. And I've given you a little outline of how to do that. So what we will have found in the previous problem is that the current in a wire is proportional to the potential difference across the wire. So here's the potential difference, V, and there's the current I. So we have the bigger the current, the bigger the potential difference, the bigger the current. And if we rewrite this, what you found in example problem 7.1, you get another form of Ohm's law, where the potential is equal to I L over sigma A. And we can write that as the potential is equal to I times R, where R is L, the length of your wire, over sigma, the conductivity of your wire, divided by A, the cross-sectional area of your wire. R is called the resistance of the material and has units, SI units of ohms. So we can note that the resistance of a material is going to depend on the geometry of the material, so its length and its cross-sectional area, whereas the resistivity is intrinsic to the material regardless of its geometry. And resistivity has SI units of ohm meters. Here's some resistivities of certain substances at 20 degrees Celsius. We have our good conductors here, our metals, silver, copper, that have very low resistivity, so they're good conductors. Insulators on the other end of the spectrum have very high resistivities and therefore are poor conductors. Now we're going to look at the concept of electromotive force. So to introduce electromotive force, let's look at a situation where we have a circuit with a current flowing through it. So here's our circuit, some source that's driving this current through the circuit. So this is the source, it's driving the current through the circuit. So it's pushing our charges through the circuit, and we're going to call the force that the source exerts per unit charge F sub S. So we can define now the electromotive force, or EMF, of the circuit as the line integral around the circuit of the force per unit charge dot dl. Okay, so that's the definition of the electromotive force of a circuit. One thing to note is that although it's called the electromotive force, it is not a force, but the integral of a force per unit charge. So examples of sources of EMFs. The source could be a battery, could be a piezoelectric crystal, could be thermocouples, it could be a photoelectric cell, it could be a Van de Graaff generator. What we're going to focus on is a very important EMF source, the generator. So generators work by having wires move through a magnetic field. And this kind of EMF, this kind of electromotive force, is called motional EMF because we have moving wires. So we're going to look now a little closer at motional EMF. Let's look at the situation where we have a loop of wire that's perpendicular to a uniform magnetic field, and the magnetic field, let's say, is pointing into the page. So here's our loop of wire, and it's in a magnetic field pointing into the page. So initially we have no current in the loop. Then we move the loop to the right with the velocity v. So what's going to happen in this case? Well, the electrons in the loop, they're moving to the right, and they're in the presence of a magnetic field. So we know from previous chapters that moving electrons in a magnetic field feel a magnetic force. That's equal to minus EV cross B. V, the velocity of the electrons, B, the magnetic field. Okay, so in this situation, we can find the magnitude of this force, EVV sine theta. The electrons are moving in a plane perpendicular to the magnetic field, so that theta is 90 degrees. So we just get EVV for the force on these electrons, the magnetic force. The direction of the force on the electrons in this segment here, AB, if we use the right-hand rule, their V is going to the right, our magnetic field is going into the page. Our magnetic field is pointing into the page. V cross B is up, but then we're electrons, so actually this should be down. The electrons are going down. So the direction of the force on the electrons in segment AB is down, which means that the current is in the opposite direction and will be going in the clockwise direction. So the force exerted per unit charge is therefore going to be the magnetic force, EVB, divided by charge E, so just VB. So the EMF is just the line integral of this force per unit charge around the circuit. So that's going to be VBH, H being the line segment here from A to B. The B to C and A to D portions do not contribute to the current. So we find the motional EMF VBH. And that is it for these slides.